Hello guys, what's going on? It is a good day to be a jazz spacer. I'm outside and enjoying the breeze, looking at the trees and everything. It's just nice to see them waving through. Okay, I'm done. Being a Zen master or whatever. Let's go on to a configuration manifold Q, and let's define something called a Lagrangian that gives us the tangent bundle in real numbers mapping onto the real numbers. And we're going to derive the intrinsic Euler-Lagrange equations using the variational principle delta L dt. Alright? So just taking the variation of this. And we're going to show explicitly as well that by adding a time derivative df by q as a function of a smooth function, the time derivative of a smooth function with respect to the coordinates and time, this will leave the equations invariant. Alright? And we can apply this to a system with generalized coordinates and identify resulting second order ODEs. Alright? So again, Q is something we call the configuration space, and it is a topological manifold. Alright? So let's let this mechanical system again be characterized by an n-dimensional, so without loss of generality, smooth configuration. Sorry, some of the cars that drive by are a little performative. I can't spell configuration. Sorry, that car was distracting me. Smooth config. Alright. It's a smooth n-dimensional configuration space. And we can describe something called the tangent bundle. The tangent bundle looks like this. Let's say pi is the tangent space mapping onto the configuration space to parameterize possible states. Okay, with a point would be, say, Q and V that are in the cotangent, or that are in the tangent bundle, consisting of a position that is in the configuration space and a velocity that is in the tangent space associated with that position. Okay, so it's the this vector, or this velocity vector, if you will, is a lift. Now, or it's not a lift yet, but we will lift it in a second. The Lagrangian again is this smooth function from the tangent bundle to the real numbers, just emphasizing that again. And L is really just a function of the coordinates, the velocity of those coordinates that are associated to those coordinates, and time. Now, what we can do here is, what we are allowed to do now is describe something called a physical trajectory. A physical trajectory is a smooth curve, so it would be gamma by some elapsed time mapping onto Q. And the velocity lift of this curve will be the same elapsed time interval, so just whatever your clock is reading based off of wherever you started and whatever you're stopping. That would be the tangent bundle. Okay, and this velocity lift is given by the time that we use to parameterize gamma and gamma dot. Okay, and they're both functions of, let's just write it out. They're both functions of time. Sorry, that was kind of bad. But the functional associated to the Lagrangian is something that we will call the action functional. So let's say S of this path that is associated with our integration bounds, which is just integrating from the elapsed time of our Lagrangian, which gives us the smooth parameterized paths dt. And this principle of stationary action, so this is called the principle of stationary action, or just Hamilton's principle, which tells us that the variation of the action should be set to 0. And it requires the physical trajectory itself to be a critical point of this action functional. And for all admissible variations, for all admissible variations of gamma that fix the endpoints. So what this looks like is if I just have, Q1, Q2 that are assumed to both be in the tangent space. Here's gamma. We're requiring that this path itself satisfies Hamilton's principle. That's all we're doing, okay? And this would be where we can consider a smooth one-parameter family of curves. So curves that we choose to parameterize, or here, let's go with deep red. These are smooth curves that we choose to parameterize as gamma sub epsilon, where epsilon is just kind of it has no definition yet, but it's just the parameter. So we'll say this is equal to Q1, and then gamma epsilon T2, this is Q2, and this is for all epsilon. Oh, sorry, that's a 3. For all epsilon, these things are fixed. These endpoints are fixed right here. All right, and we can parameterize, more curves with epsilon that explore the space of those things. And the parameter of curves that satisfy the Hamilton's principle is kind of just forced, because if we took gamma epsilon from T1 to T2, mapping onto the configuration space with gamma 0, which is wherever epsilon is equal to 0, to be equal to gamma, right? This associated vector, this basically creates a field. It creates a field called, let's call it X. It creates an X field that we can define as simply the partial derivative of this gamma function, epsilon, d epsilon, where epsilon is equivalent to 0, that is in the cotangent bundle associated with all of the parameterized curves in the configuration space. So we essentially can describe the tangent space of the variation space of the associated variation vector field along this parameter. Okay, so we have a tangent space, we have everything, a one parameter field, and of course what's going to happen is you should be able to physically reason through the boundary conditions, which says that, well, if we have x of t1 is equivalent to x of t2, right, this should be equivalent to 0, right? That's very important. So the first variation of the action, then, we can actually really define this nicely now that we have this mental image, is if we take the first variation of the action and we differentiate by this parameterized action here, and we want to find the curve where epsilon is equal to 0, what we do is we integrate from t1 to t2 like before, but now we have to deal with the partial of the Lagrangian with respect to the partial with the, and remember we're doing this for in dimensions, so we haven't lost the in-dimensional smooth configuration. You can have I here, and then plus, and we're going to continue down along here because I'm running out of space. But del L and V sub I X, boop, boop, and this is all integrating against the time variable. That's not an epsilon. That's a time variable, right? Where all quantities are going to be evaluated along the curve of gamma, and the summation over the repeated indices would be implied. So what we can do is integrate this second term here by parts, and then we'll factor out whatever is remaining of the vector field, of the variational vector field. Okay, so let's go ds is, or let's not do ds. Let's show that. Let's just write it out again. So we'll go 1, 2. Del L by del V x dot dt, and then we can say that this is V and this is U for the integral by parts, so we'll have V, that should be a V, and then integrating the vector field, the derivative of the vector field is just the vector field, evaluating from t1 to t2, and then we'll subtract off this extra integral, which is the v du part, dt of this. Alright, am I missing anything? Oh, I'm missing x, or v. Yeah, perfect. Alright, so now that we have this integral, and remember this minus sign is just, it's still the right hand side of the equation, I just lost space. Okay, so what we can do now is we can factor out this quantity here and this quantity and create the variation. We'll truly define what the variation symbol does here, which is that it allowed us to factor out the variational vector field, and qi minus d by dt of the Lagrangian, just a gamma, whoops, of the Lagrangian, and this should be, let's go dv, okay? Because what this is kind of like just finding associated or generalized momenta, dt, which is equal to 0, okay? So this is like a generalized, like, momenta. It's a change of the Lagrangian with respect to velocity, and then we have a change in the Lagrangian with respect to the coordinates, which give us basically like this potential like term. But this has to hold for any variational field here, all right? And since we're equating it to be equal to 0, right, with Hamilton's principle, by extremizing this action, just in general, it's extremized, we can just say, well, this here should go to 0, right? That should go to 0. So, and we can, this is the Euler-Lagrange equation for, I is 1 to n, all right? And this is said to be the Euler-Lagrange in local coordinates, okay? To the Euler-Lagrange in local coordinates, and intrinsically the fiber derivative, we're going to find something called the fiber derivative. So if we take f on L would be the cotangent, the tangent space mapping onto the cotangent space, and this is how we can intrinsically assert that along some physical curve, gamma, right? So let's go back to our gamma. along some physical curve gamma, the covariant derivative of the momentum section, which looks like the gamma and gamma dot, the velocity lift, and the gamma path, balances the vertical. It has to balance the vertical differential of the Lagrangian, of the differential of the Lagrangian itself. And so to establish something that's important called, well, what this looks like in practice is you would define a Legendre map here that goes from the velocities to like the momenta. Mathematically, we can be general, but let's just assume physics for now. What would happen is we can define a type of bilinear form in general, or an inner product. In this case, it would be just a general bilinear, because the inner product has other positive definite type and symmetrical arguments. But what we would have here is the derivative of the Lagrangian with respect to the velocity. That's a function. So it's the derivative of the Lagrangian, the partial of the Lagrangian with respect to this as a function itself, dotted or evaluated with W, where W is in the tangent space at that point, if that makes sense. Okay? So now what we can do is go a little bit further. We can define something called gauge invariance. Okay? Gauge invariance. And what this looks like is if I have if I want to do a transformation upon this Lagrangian function, I can write it as unique up to a total time derivative of a smooth function, where we evaluate it from configuration space to the real numbers. All right? And it's this also is an arbitrary smooth function in general. Once we do that, then we can say, well, from this, let's just use, instead of in dimensions, let's use k for k dimensions. So let's say we have a totally different Lagrangian that we're changing. So we're going to want to evaluate the partial of this Lagrangian with respect to the position, which will give us the partial of the Lagrangian times the second differential here, acting on f, and then times qi. Alrighty. And this would be qi dot plus the other cross term here. This is just trying to make sure that we are doing this correctly. Let's make this f here. Okay. And then we can take these two cross terms and kind of get a nice form for the derivative as well with respect to the velocity at k. So we're just basically defining the transformation laws plus del f over del q here. So these are the transformation laws on how these Lagrangians that are transforming should preserve this structure here. Now differentiating with respect to this changed Lagrangian, or this transformed Lagrangian, should give us a new kind of Euler-Lagrange equation or system of equations, but this time we have these extra terms, del f by del q by del I, qi, q dot I, plus this here. And it's important to understand now that if we subtract, if we differentiate then this expression with respect to time, and also just subtract how we got these transformation laws here from each other. So boom, boom, and also boom. Combining everything so that we get the nice Euler-Lagrange form should look something like del L prime by del Q K. Yeah, so this will go away, this will go away, and we should be left with basically identical Euler-Lagrange equations. Yeah, I mean, they're basically identical. So this gives us the idea of gauge invariance. Let's see. Oop. Just wanted to double check that for myself. So yeah, there's an Euler-Lagrange equation on this side, and there's an Euler-Lagrange equation on this side. Isn't that lovely? Right? So we transformed it, but everything kind of like under, you know, some smooth function that's arbitrary, we still were able to transform the Lagrangian but get the same basically additional terms that cancel identically. The Euler-Lagrange equations for this are identical to those for this one. So equivalently, the action is going to change only on a boundary term. So this boundary term looks something like f of q t2 minus f of q t1 t1. And this doesn't affect the it doesn't affect the variational principle. Okay, for fixed endpoints. Okay, so that's how we know this, just by just computing it out. We don't have to rigorously prove it yet, but I mean, just intuitively, and we know how it works. So if you expanded the total derivative to separate though the equations, this is kind of the interesting part. It turns out that if we wanted to expand this out from k to, you know, in general functions of I, then that would look a little bit different, because if we have an n-dimensional system and then we have, you know, some m-dimensional system, or maybe not m, let's just stick with the indices of I and j. What we can have is something like this, where we explicitly talk about the accelerations, which would be q dot I, q dot j, and let's stick with q double dot here, and q dot I, qk, L of Lagrangian. And remember, I'm getting this from computing out this time derivative, okay? And q dot is just simply the time derivative of the coordinate in configuration space, plus ql q dot I del t minus dl over dq I is equivalent to 0. Okay? Now, what this tells us is this defines something. Well, we can say if the Lagrangian is regular. Oh God. Which a regularity in the Lagrangian sense just means this this Hessian matrix, this is called the Hessian matrix, it gives us information about the convexity of the particles, or the kinetic energy, if you will. The Hessian matrix is invertible everywhere, and it's going to be positive definite. The system can be solved uniquely for second derivatives. So, in other words, the second derivative for the acceleration, the jth acceleration, is unique. And it would yield a well-posed. This also gives us a well-posed ordinary differential equation in second order. Okay? And this essentially is a second order system of arbitrary differential equations on the configuration manifold. Alright? So we've exhausted what we could out of minimal structure, and it always comes back to the configuration space. So for example, how to think about this, just a bookend. If you have some pendulum, let's just say this. The configuration space of a pendulum would be S1. It would be the one sphere. Why? Because if you were to just, it's a one-dimensional line that just wraps around in on itself. But it's just how we talk about topology in general. This goes way back to, the configuration space and it being a topological manifold at the very beginning of the episode. And this is just one simple example of a system. But you could also do something which also gets worked out in Landau's mechanics book from the very first get-go. One of the first problems is, man, they are road raging. One of the first problems is a double pendulum. And of course, there's an accessible amount of states that this thing can be in, but also there's another accessible amount of states that it can be in, and this creates another manifold, okay, and constraints. So anyways, that's how we think about this. That's how we think about classical physics. So this episode, just to recap, we talked about variational mechanics and why variational. Oh, and one more thing. This right here is what we call the fundamental lemma of variational calculus, right? If you want to formalize it mathematically. This is the fundamental lemma of variational calculus, which states that this guy here goes to 0 because of the space of all admissible variations to be equivalent to 0. We force this to extremize the action, or Hamilton's principle. Okay? Thank you for watching.